Hello friends, today we're going to talk about the famed brick wall filter. This is a brick wall filter that I've already designed in Scope FIR. And these are called brick wall filters because the transition band between the pass band here and the stop band here is extremely steep, which is analogous to how a brick wall rises straight vertically. Now in reality, in filters, you can never have a transition band of 0, which would be, in the brick wall analogy, a true vertical rise. But what you can have is a very steep transition. And essentially, the number of taps in a FIR filter is related to a variety of parameters, but one of the most important is this transition between pass band and stop bands. So to give you a little tour of this filter, we've got 1 kilohertz sampling rate, nearly 10,000 taps, which is the minimum number that can meet all the other specifications, a passband upper frequency of 0.1 kilohertz, and a stop band lower frequency of 0.1005 kilohertz. So the transition band is this difference between the stop band lower and the pass band upper. So if we take the stop band lower frequency, subtract the pass band upper frequency, and convert from kilohertz to hertz, we get 0.5 hertz as our transition bandwidth. So this is a very steep filter, but it's not a brick wall in the literal sense that there's no transition band whatsoever. We've got a passband ripple of 0.01 dB, which is extremely flat, and we've got a stop band attenuation of 80 dB or greater. So we can see on the frequency plot that all of the specifications above have been met. Let's zoom in on our transition band to see what's going on there. So having zoomed in, we've automatically converted our units to hertz to make it a little easier to relate to in the plotting. But basically, this is that 0.5 hertz difference between the top of the pass band and the bottom of the stop band. You can see that this has a nice smooth curve to it, even though at the original zoom point this looked perfectly straight. Now over on the impulse response, just looking at it from this point of view, you've got this very steep spike in the middle. You've got some ripples around the edge of the center tap, and then you've got what may be perceptible as some little wiggles here. So we'll kind of zoom in on each feature of that. Now at this resolution, it appears that all of these taps on each side of the center are essentially 0, but that's kind of a illusion from the graphing limitations of the computer screen. Let's zoom in towards the center and see more what's going on there. So we've got these things that are kind of damped sinusoidal, visually speaking. And you can see that these head towards 0. So if you kind of continue this trend, you would imagine that these ripples continue, but they just get smaller and smaller in magnitude. So if we zoom back out again, let's zoom into the far low end of the graph. As I had expected, this damps towards 0. There's a little ring at the end of it. And since this is a linear phase FIR filter, we can predict that the other end of it will be symmetrical in a mirror image sense. So we knew that going in. You'll notice there's this one point that goes off from kind of departs from the pattern, and that relates to the equiripple aspect of this filter. This was designed using the Parks-McClellan design algorithm. We cover that in more detail in other videos, but it has a few characteristics that with some experience you can recognize. It has this equiripple, as it's called, characteristic in the stop band. In other words, all of these ripples are at the same height. In the pass band, it has a ripple that's constant around a center point of 0 dB. And then also on this far end, as we've seen, it has what looks like an anomaly, but that's actually to be expected with this type of equiripple design. Next, let's do a similar design, but using a different design algorithm, which is the windowed Sinc algorithm. Here's a similar design using the windowed Sinc design method. I've picked the same number of taps, set the cornered frequency at 0.1 kilohertz with the same sampling rate of 1 kilohertz. And we'll zoom in on this to kind of get a visual comparison. We'll look at the pass band. It has a different ripple characteristic. Instead of being equal, it's all, I happen to know it's all kind of lumped into this area near the corner frequency. In the windowed Sinc design, the frequency characteristics of it are determined by the corner frequency, the number of taps, and the window type that you choose. I've chosen the Blackman-Harris 4-point window here. You notice our stop band is a lot deeper here. The program maxes out showing you anything greater than 130 dB of here, which is what this flat line is depicting. Well, let's zoom in on our transition band and see what we've got. We've got a transition band that looks roughly comparable . You can see that something begins to happen here at about 0.2, and then we get to, just to be consistent, we'll judge this against the 80 dB point, which is 0.4. So this difference between 100.4 and 99.8 gives us a transition of about 0.6 hertz. So that's comparable to what we had before. And depending on what you're trying to do, this might be considered a better design. And the only thing it has kind of as drawbacks compared to the other one, we've got this kind of uneven attenuation near the edge of the beginning of the stop band. So in a lot of ways, this could be considered a better filter design than the other one. Honestly, either one of them would probably work for whatever application they're intended for. But the thing to notice here is this takes nearly 10,000 taps either way. And in the scale of FIR filters, 10,000 taps is really an extremely large number of taps. Some FIR filters have as few as 10 or less even. Kind of a high number that I use as a rule of thumb is 1 or 200. If you're using a filter that has this many taps, it's probably either some sort of extreme design requirement, or else you may be overdoing it in some way. So in processing and memory terms, we have to store nearly 10,000 previous samples, and in this scale of 1 kilohertz, that would be nearly 10 seconds worth of data. And also, for every sample that comes in, we have to calculate a FIR filter having 10,000 taps. So as kind of a simple metric, you could think of that 1,000 multiply accumulate operations. So the delay through a linear phase FIR filter is number of taps minus 1 divided by 2 in terms of samples. So just to work with some even numbers, let's call it 10,000 taps divided by 2 is 5,000 sample delays at a 1 kilohertz rate, comes out to 5 seconds. An intuitive way to think of this is we need a lot of data in order to make this sharp distinction between the very top edge of the passband and the very bottom of the stopband. In other words, how can you tell those two frequencies apart conceptually unless you've got a lot of data to work with? So you're paying a price here in 3 different ways for this brick wall filter. You've got a lot of data storage, you've got a lot of delay, and you've got a lot of computation for each input sample. Now if we want to go farther with this, we can. So let's put in 15,000 taps and see what happens here. Let's zoom back out to the top. We'll zoom in on this, and what we got was a transition band, let's say, kind of visually speaking, about 0.3 hertz. So that kind of fits together. We went up to 50% more taps and we got something like 50% less transition band. But again, we paid a higher price in terms of the number of taps and those other issues of computation and delay. So the lesson here is that you can have a brick wall filter that has an arbitrarily steep transition between the passband and the stopband. What you can't have is a true vertical, as in the literal brick wall that's truly vertical. The more taps you have, the steeper that transition is going to be. So let's go down to the other end. We'll go to a very small number of 100 taps. You can see that over the same frequency span, it's gotten a lot broader slope. So visually speaking, this one appears to be about 60 hertz wide from here to here. And depending on how you look at it, you could call this a brick wall filter. It's not vertical, but it's relatively sharp as a fraction of the overall sampling frequency. It's not vertical like a literal brick wall, but then again, the other one wasn't either. So the brick wall idea is more of a metaphor than anything that we can hold to any kind of strict standard. And I think in any kind of reasonable sense, you can say, yes, there is a brick wall filter, but you have to be a little bit flexible on what you mean by a brick wall. That ends our video for today. Thanks for watching, and bye-bye.